So Rutherford's experiment, he fired alpha particles at thin gold foil, and Rutherford found that most of the alpha particles passed straight through the gold foil. And this suggests the atom is mostly empty space. However, some alpha particles, in quite a small amount, were deflected and an even smaller amount reflected back from the gold foil. For this to have happened, remember the alpha particles are high energy, radioactive particles, they've got lots of energy going in. And if they're going to bounce back, then they've got to be encountering something with a large mass. So most of the mass of the atom must be concentrated in what we now call the nucleus. And because it bounced back, that tells us it must be positively charged, the nucleus, that is. So that's how we get a Rutherford model of the positive nucleus with the electrons in orbit round about it. And later on we're able to show that there were also neutrons in there with no charge, and these dots here represent electrons in orbit round about the nucleus with a negative charge. Okay, that's known as the Rutherford model of the atom. And way back in second year we introduced the idea of atomic notation, where you have for each element X, you have A, an atomic number, and M, a mass number. Which is the combined number of protons and neutrons. Collectively known as nucleons. X is the element, and A is the atomic number, which is the number of protons, which is what defines each element. So any material with, for example, 6 protons is what we call carbon. Doesn't matter how many neutrons, so we can get isotopes with different numbers of neutrons, but the atomic number defines the element. And using this we can write nuclear decay equations. I'll show you a few examples in a second, but in order to get the hang of that we need to get the idea that An alpha particle can be written as 4,2. It's the helium nucleus, basically. A beta particle can be written as 0, -1, because it's an electron rather than a proton. No mass, therefore. And gamma doesn't have atomic notation. It doesn't have mass or charge. So using this, we can give some examples of nuclear equations. So examples. Polonium-212 emits an alpha particle. What daughter nucleus is produced, or what daughter product? So the atomic number of polonium is 84. So we start with 84, 212 polonium. We know that it emits an alpha particle, and we can write that with the alpha. I'll just show you can sometimes get it written as AHE plus our unknown. And basically the atomic number and the mass number both need to be balanced. So we know our unknown mass number plus 4. So 212 is equal to 4 plus m. That's the mass numbers. And 84 is equal to 2 plus a, the atomic number. So rearranging them, we get m equals 208 and a equals 82. And if we use the 82, we go and look up the periodic table, which tells us it's lead. So our final answer for the daughter product is 208, 82, and from the periodic table, Pb. So that's our daughter nucleus. You can turn these examples around the other way. So 212 bismuth decays into polonium-212 via emitting a particular particle. So which one must that be? So balance once again. So 212 on the left side for the bismuth must equal 212 plus the mass number of our unknown, and the 83 on the left hand side must equal 84 plus the atomic number. So that gives us that the mass number is 0 and the atomic number is -1. So therefore the emitted particle is 0 - 1, which we can either write as E or beta for electron. And the idea here that we've ended up with polonium is actually not that surprising. I know we used it in the previous example, but we quite often do get what are called decay chains like that. So you start with the bismuth, you go to the polonium then goes to the lead, which is stable. So you quite often get sets of decay like that as well. Now these atomic mass numbers and atomic number calculations are very much rough calculations. When we look at the mass numbers, the mass values in detail, what we find are slight differences. So the one that we've just done above there, the bismuth into the polonium, the electron, the beta particle comes out with energy. That energy must be coming from somewhere. And when we look at the detail of the mass, we find that there's mass missing, essentially. And so that's where the energy comes from. So kind of 3 and 4 we do together, because 3 introduces the idea, I suppose, and then 4 does the calculations of it. So when detailed, find that some mass, and the phrase is often used, is lost. In nuclear reactions. That lost mass, or mass loss, sorry, is converted into energy via the most famous scientific equation, E equals mc squared. Now, we can look at that in a bit more detail. We can look at that from the idea of fission reactions and fusion reactions. So fissions is when something splits. So the one up above there, the bismuth producing polonium, the bismuth is split into polonium plus a beta particle. So that's an example of a fission reaction. But you can also get fusion reactions, which are defined when lighter elements join together to create heavier elements. So we'll give those definitions here as well. So fission occurs when a large nucleus splits into two nuclei of smaller mass number. Fusion occurs when nuclei of smaller mass number join or combine to create a nucleus of a larger mass number. And we'll look at worked examples of that next. So you'll see in this example we're given the detailed values of mass. The neutrons, we've got to watch them. They may be included in the table. You might have to look them up in the data sheet. The stuff like the mass of uranium, molybdenum, xenon and so on, they would be given in the question. And what we need to do is then to work out the mass on the left hand side. Sorry. Just adding up. So we've got the uranium plus a neutron. And remember, don't do any rounding off until we get to a final answer. Did I say electron? I meant neutron. So total mass on the left hand side. And similarly, the mass on the right hand side. Go back to the original formula. Molybdenum, xenon, and we've got two neutrons. So all this data out the question. Adding all that up. Okay. So the mass loss is the left hand side minus the right hand side. Now it's a good check. Your left hand side should always be greater than your right hand side, because otherwise the change wouldn't happen. You can't gain mass. We can convert mass into energy, but you can't spontaneously gain mass because the energy for that would need to come from somewhere. So you can convert energy into mass, but you've got to make sure that that energy is supplied, so it's not going to just happen spontaneously. And all of that, you might be better just putting the times 10 to 27 in each bit. Your calculator might display this as 4.25 times 10 to minus 28, that's okay. But now we're ready to use the Einstein equation. Don't forget the squared bits. Plugging all that into your calculator. So we get that energy from one reaction. Doesn't seem like a large amount of energy compared to you or I in the kind of everyday lives, it's not. But at a nuclear level, this is a large amount of energy in nuclear reactions because the strong nuclear force and the weak nuclear force are amongst the largest forces in the universe, produce much more energy than other types of reactions that we'll study in the rest of the course. So these are relatively large numbers. We'll do another example here of a fusion reaction, but the calculations are exactly the same. So the mass of the left-hand side is the tritium, as it's called. It's actually this isotope of hydrogen. It's got a name of its own. And so is the other one. The hydrogen 2 is known as deuterium. Here's the total mass on the left-hand side. And the same on the right-hand side. Incidentally, if you ever find reactions include electrons, we would ignore them. They're too light to contribute significantly to they're not part of the nucleus anyway as well. So the right-hand side is alpha particle. And the neutron. And now we can work out the mass loss. Remember not to do any rounding. And like I say, your calculator might express this as 3.1 times 10 to the minus 29. It's all the same thing. And now we can use the E equals mc squared equation. Don't forget squared. And this is the standard reaction actually taking place in most stars, what we call main sequence stars. So combining hydrogen isotopes to create helium, alpha particles. So learning outcome 5 is about knowing how a fission reactor would work. I don't think you would be expected to kind of draw something like this from scratch, so it's quite likely that we maybe give you this and ask you to comment on maybe even just one or two parts of it. But we'll go through the main parts. Okay, so the fuel rods. And they contain the nuclear fuel. involved in the fission reactions. So you've got your heavy elements, which will naturally split, right, or spontaneously fission, is the technical term of that. You also have control rods though. And they're used to absorb some of the neutrons. From the fission reaction to control how many more reactions will occur. And ultimately that's there for controlling the total amount of heat produced. If you didn't have any control rods, and you would get the idea of meltdown, that you'd very quickly, if one reaction produces 3 neutrons, that produces 3 reactions, 9 neutrons, 9 reactions, 27 neutrons, etc. You get exponential growth in the number of reactions taking place, and therefore exponential growth in the amount of energy being produced. And that would be an uncontrolled chain reaction. So control rods are all about controlling the chain reaction. You also notice here the mention of the graphite core, right? And that's called a moderator. So a moderator slows down the neutrons produced to enable them to cause more fission reactions. Okay, if the neutrons are going too fast, they don't actually cause more fission. The coolant heat from the reactions to a boiler where steam is produced. So we want heat, but we don't want it all just to build up inside the reactor, or it'll make the reactor melt. So we're taking that heat away. So we're not making heat so we can then cool it. We're making heat so we can use that heat to do something like produce steam, which in turn can produce electricity. And then lastly, you have what's called a containment shield, which is the mixture here of the reactor vessel and the concrete shield. And the containment shield protects the surroundings, partially from radiation, but also acts as a safety were it to explode. So it tries to contain everything within this area. So you've not got bits of reactor flying around. That's a quick run through the ideas of a fission reactor. And we do the same idea now with the basic concepts of a fusion reactor. So fusions, remember, taking a lighter element, so usually it's stuff like hydrogen that we're trying to join into helium. So we're kind of trying to replicate the sun, the reactions of the sun on Earth. So a few problems to overcome. So first of all, in order for the fusion to take place, the hydrogen has to be at very high temperatures. Hot enough to be a plasma, which means basically all the electrons have been stripped off and your atoms broken down into separate nucleus and electrons. But the problem with that is it's so hot that you couldn't put it in a standard container. It would literally just melt the container straight away. Okay, so we've got this problem of containing it. And there's a few different solutions. The kind of two main ones being explored just now are magnetic containment, so tying in with the work we did earlier on magnetic fields. But you can also get what's called inertial containment, which uses light. So this means it can't be held in a traditional container. So magnetic containment uses magnetic fields to hold the plasma in place, and as we saw in the previous chapter, that will result in the charged particles undergoing circular motion. So you contain all of this in a big donut shape basically, and the plasma goes around it. It's called a tokamak. You met it briefly in Nat 5 as well. And inertial containment uses laser beams, it uses light to hold tiny amounts of plasma in place. But as we saw, you don't need very large masses to get significant amounts of energy involved.